All right, welcome everyone. So this is a quick tutorial regarding the lab component of week 4. And on my screen here, I have opened the Jupyter setting. You can also try a Colab environment, but essentially when you go to week 4 and you extract the lab component of it, you should see a notebook, a bunch of different files that we're going to use, and also a PDF format of the same file. So you can double click and open it this way. So this is the PDF file, and it'll tell you on what to do, what are the specifics of it, and so forth. Or we can also directly go to the Jupyter Notebook, and it is commented quite well. So you can just try that out. So again, hit open in there. And should take a while to load up again. As you can see, there's already a bunch of different outputs here. Typically, it's like that if it's been run earlier. So sometimes you can just do go to kernel and restart kernel and clear outputs of all cells. So it'll do a restart and everything should be gone. All right. So as we know, one of the first thing we need to do when we get information is turn that into insights. And once you have the insights, you can create that as a knowledge so that you can make decisions. So files that are structured in a format that's usable for machine learning or analysis is something we call information. Some trends, some patterns that we observe from the information is what we call insights, and that insights is going to be turned into some actionable items. So it is what we call knowledge. So the purpose of this lab is to do multiple different things, and it might seem a little overwhelming, but that's okay. It's just a start. At the very least, you should be able to master the concept of descriptive statistics. So as we can see here, there's a bunch of text that I put. So the purpose of the lab essentially is to do descriptive statistics, univariate analysis, bivariate analysis, and that also using some built-in data set, the iris data, and also some data set that we'll be importing from this structure here, the Gapminder and stock. So the way the notebook is structured is it will say certain parts that kind of ensure it follows this step here, and part A, part 2, part B, and so forth. So the first thing we'll be doing is importing a data set. And one of the things with Python and any other programming languages or data science centric programming languages are or Python is that you will see some built-in data sets that's for you to practice. I'm just going to slightly improve the size of the font here. So import pandas as PD. It's standard library that we're going to use. From sklearn.dataset, it's a built-in dataset, and there's something called iris dataset. If you Google iris dataset, it is freely available dataset that has some information about the flowers. So the third one is matplotlib. We'll be using that as our plotting device, and also some scalar matrix. So just hit that run. And again, in some cases, you can also always create this file. So put this library to start with. It doesn't hurt. Pandas, matplotlib, and these kind of things, you'll always need it anyway. So might as well put it. I mean, the iris data set, you may or may not use it all the time, but again, it's always good to have. So that being said, the second code here is establishing a figure size. So essentially, when we create different diagrams or visualization, they might be of different sizes. So what this is telling you is that whenever you use matplotlib, ensure the figure size is by 10 by 6 inches so that you get different stuff. If you don't put this, it'll still yield visualization, but you can alter it. You can say 12 by 8 or whatever you want. And this is a standard. The 10 by 6 is just, it looks nice on the screen here. So let's run that. Again, this is totally optional here. Right, so this is optional. I mean, setting up figure size. Okay. So iris is the name of the data set. Iris load.iris is a function. Essentially, what they're saying is create an iris data set, data frame rather, and grab it from iris. So this guy here. And once you grab that, turn it into a data frame of some sort, because we need to do that. Typically, when you import the file, this is the step that is not needed, but let's do that, and let's go ahead and do that here. Okay, so it ran properly. So all of a sudden, you see that bunch of files have run properly. And you can ignore this. This is Grammarly stuff. So this is nothing to do with the coding here. So iris is a data frame, or iris dot is a data frame. We want to know some of the features of this data set. So feature essentially is columns, right? So we call it columns. So the way this file is structured, this is how it's structured. So you have a bunch of different stuff in sepal length, sepal width, length, width. This is structured this way. That's what it's saying. You want to know what features they are, because at some point we'll start to do predictive analytics. So just giving some ideas is feature dot underscore names. And this iris data frame that we extracted from iris here, same command, iris underscore data frame dot head dot 5. So show me first 5 items. So here, so this is the row order. So 0, 1, 2, 3, 4, 5. The first is sepal width, petal width. So iris data set is a common data set that is used in machine learning activities or language for us to use practice data set. If you wanted to use and know the shape of the data set here, you would just do data shape. So you can see there are 150 rows and 4 columns. If you wanted to know the data types, you would just do data types dot data types. In float is kind of number that we use, right? So it has a length, like it would be 2.345678, that kind of stuff. It's not a whole number, right? So once again, the first part of descriptive analysis is we do a bunch of different things. And the descriptive analysis is the idea that you will be using the look of the data. So think about it, right? If you were if I gave you a number, a bunch of a spreadsheet, and I asked you to deduce some intelligence based on that, it'd be quite difficult. But if I asked you to visualize it, it's much easier, right? So if we gave you a data set that looks like this, it's hard to for you to figure out what this means. It's difficult. But if I'm telling you a distribution of data, which this means that most of the grades are here and some are here, and then least number of them here, then it's easier for you to know the distribution. So descriptive analysis gives you some idea about what historical or what has been to the data, or or do we have. It explains the data. So some of the key components of descriptive analysis is you will know some mean, average, mode, like median, standard deviation. You will also know distribution of the data from a visualization point of view. You'll also figure out some of the outliers, if there are any. Outliers are things that are not fitting to the distribution. So for example, if there are a data set, most of the numbers fall between 1 to 100, and 1 comes around 1 million, that is an outlier. That is something that we may or may not need. So first thing we do is something called, again, you can use SwiftViz to do this, or you can use your the friend from Colab. Either way, it's fine. So some of the first things we do is something called histogram. And histogram here essentially saying use this iris data frame dot hist and bins equals 20. And I'll talk about what that means. So if you hit that, it has 4 variables, and it created a histogram of all those 4 numerical variables. So a bin is, for example, so if we have millions of data, and let's say if you have millions of data, it's hard to see it in here. Like it'll kind of like look like this, right? A lot of different data. So what we can see is divide those millions of data. Sorry, let's 1 million data into 10 pieces. So 1 to 2 million would be here, 3 to 4 million would be here, and so forth. And we can say there are 5 observations that are between 1 to 2, 6 observations that are 3 to 4, 5 observations, 7 to 8, and so forth. So it gives us better distribution. So if you don't put bin explicitly in this little thing here, it will just decide on its own. But I said bin 20, you can do bin 10, whatever you want. It will kind of look different depending on the distribution, right? So at least to give you some idea, look, if you like a simple length, looks like most of it is around 5.5 to 5 here. This range least is beyond 7.5. So all of a sudden, like looking at this data, as opposed to this here, this gives you better idea. That is one of the key things about descriptive analysis. The other thing we can also do is probability distribution. We have a plot name called KDE, or kernel density estimate plot. It is an example of a probability density function, PDF. We talked about it during the class. So it deals with continuous random variables. So if you're running a marathon, you may finish it in 3 hour, 4 hour, 5 hour, you don't know. So it is continuous. It has no boundaries, so to speak. If you wanted to monitor the data, like, if you look at the data itself, it has continuous, right? This is not limited. It could, in some cases, could have 10 standard meters. So we can see the distribution, and what distribution tells us is that for 4 variables, perhaps for this orange line, which is sepal width, it looks like most of the stuff is happening around here. There's a probability of happening between 2 to 4 quite high, right? So you can find the probability distribution. So it gives you some shape of the idea, as opposed to just, again, looking at the numbers. Now you're looking at shapes. And you can also describe the data. This is, a quick summary of things. So you can tell you mean, standard deviation, mean, 25 percentiles, 50, and max. So very quickly, using this describe button for a numerical data set, you can look at the stuff. If there is some data set that has categorical data like school, it will not provide you that information, right? So it has to have numerical data. The other thing we can also do is create new synthetic data. Synthetic data at the purest form is fake data from a distribution. So what does that mean? So let's think about it this way: is let's say you have this data set, and the data set was turned into a distribution like this, meaning that most of the content are here, some are here, and some are here. Now, this is real data, and this cannot be used in real life, and we want a fake comparable data. So we'll be trying to find fake stuff, but we will be creating same distribution. And what that means is a lot of characteristics of data will be covered by this one. And it is what we call synthetic. It is true. It is a representation of the real data, but it is not actual observation. So if I look at your grades and I say the average is 50, the high is 90, and so forth, I can create a fake data with fake names and ensure that I can do machine learning without you worrying about your privacy. So again, NumPy is a numerical library used in Python. Let's run that. And there's a random function that we can create. So essentially what this is doing is you're creating random functions randomly, starting with period 2000. This is also going to be what you call a time series data set, and equally spaced in 1,000 periods. So we are going to just grab this stuff and then create random generation. This is a built-in function. It is using NumPy, 1,000 pieces, and period 1,000. So let's run that. And ts.plot means plot this little data frame. So let's look at how it looks like. And it looks like, starting from January all the way to July, 1,000 pieces. The data is all over the place. Some -2, some it's all random. If you run it again, it should probably look something a little different. Every time you run it, it should be different because it's random, right? So again, we can create a bin. So, transform data. So we can create a bin equals 80. So 80 pieces. And look at this, the distribution. It looks like your data is somewhere falling. Most of them is falling in around -1 to 10. So it's very less data as well. We can also do box plot of the same data. So, let's do box plot here. And what box plot tells you is that so box plot tells you simple. It's sometimes called box, and it's sometimes also called box and whisker. Essentially, what it tells you is that your 50% of the data is in this box. So this is 25% and this is 25. The green line here is what we call median. 25% of data is here, quartile, and the other 25% of data is here. These little dots are outliers. They do not belong to this original distribution. These are things that are million. If you have data set that has from like 1 to 100, these entries are 1 million. Like these are somewhere. We can throw this away. So one of the things that we do is we remove outliers, because outliers are nuisances sometimes, right? We don't really care about them. So it also visualizes, rather than just searching and looking for different numbers, we can also quickly do box plot. So again, so far we've done describing the data, mean, mode, median, sorry, not mean and max min, something like that. We've also done histogram. We've also done some probability distribution. We've done random number generation and box plot. That should give you some idea. Again, we can describe this data, and you can look at some ideas in here. So, count is 1,000, mean, max, and so forth. So very quickly, you're able to figure things out. Now, next 3, 4, 5 distributions are beyond the mathematical scope of this course, but very least we can just quickly talk about it here without paying too much attention to the math itself. So there are many different types of distributions, and distributions are based on things we want to achieve. And we have something called triangular distribution. Normal distribution is something you hear quite frequently. A lot of things in life are normal. And what it means is that if you are if you find, let's say if you go and do survey of 100 people, and ask them heights, right? And then you kind of put them like you draw them out, and let's say this is 5 feet and like this, and then you say some are 5'1", 5'2", some are 6, some are, so typically you can just draw it out like this, right? Just very simplistic example. And some people are let's say quite tall, right? So some people are super tall. Most of the guys or most of the girls or individuals are somewhere like 5'8" to 5'11". So if you do a distribution like this, it looks like this. So this is what you call normal distribution, is that most of the people are very close to the mean. So you find people that are super short in your life, think about it, and you also find people who are super tall, but they are a very small portion. Most of the people are very close to the mean height. That is the establishment or theory of normal distribution. This is what you see. But there are other distributions as well. Again, this is beyond the scope of the course, but very least I can also kind of talk about this. One is something called triangular distribution, where the values between low and high are equally likely. So, I'm giving a value of 10 and 90. And 20 is something that appears quite often, mode, right? The thing that appears. So based on that, we can also create a distribution. So let's go ahead and create that here. First of all, we want to create some random value. So again, I'm creating some triangular distribution value based on upper value, mode, and upper value, sorry, lower value, mode, and upper value, and I'm saying create 1,000 of those. Okay, and then we can create a plot, something like this, and it will come. And if you see, if you note, I'm telling it is that 20 should appear the most, and it did, right? So if you go back here, 20 should appear most, and 10 and 90 area have equal probability of appearing. So there's another distribution, and something like that, right? So we can again describe it, again, same theory, describing it. We can also use another distribution called geometric distribution. It's like it's the idea of you finding success and failure. So if you're flipping a coin and if you think heads is going to come, you have 50% chance, and if you think it's tails, it's 50%. So success is defined as what you want, what you're looking for, right? So if you're thinking to get heads, that would be success. So it also monitors. So it gives you some variable. Again, I'm not going to go into math, but just kind of giving you some of the uh, some of the idea. Again, you can generate random data here, and again create some sort of descriptive analysis here as well. Okay. So it looks like, the frequency of you getting one is quite high, 5,000, and rest is going to be quite low. The other one is Weibo. And again, I'm just going to run this describe button here. Again, a lot of these distributions, we don't care just yet, but I'm giving you some of the tools that we're going to use over the course. So Weibo is another distribution. You can think of it this way as something that is used in engineering and fault analysis and projection. Like Weibull is used sometimes for earthquake prediction and things like that. Again, it's creating a random variable using Weibull distribution. You can do the same thing and run it and so forth. So again, it takes over property. So what are we doing here? All we're doing is we're creating fake data and seeing how the data shapes depending on some of the variables that we're providing here, right? Again, you can describe the data. Feel free to use other tools as well. The other stuff is something called uniform distribution. So, if you're catching a bus, and the example that I have, and at a random times, and you have equal probability that the bus can come at 7, 8, 9, 10, 11. So that is what we call uniform distribution, meaning that everything has equally distributed. So again, I'm creating random fake data here, and it's split into 200 bins, and it should yield something here. So it's, and when you look back as we're going through this, you can see how the distribution changes, right? So uniform is consistent. This one is shaped a little differently. This one is shaped a little differently, and so forth. That gives us idea on what kind of distribution does it have. One of the things also we want to do is look into what we call a stock market data. So if you go back here, there's a stock_px, and it just import the file here, right? This is a choice between header or not. If you take that out, it's also fine. So let's run that here, and it is going to give us date, and then this American Airlines stock, Apple, General Electronics, IBM, J&J, and so forth, right? So it looks like a time series data because it is equally distributed. So let's describe the data here. And it again can give you very quickly everything. And let's do a box plot of every different company here, right? So you can see that the range of SPX, which is the index, it's quite prolonged. Obviously, the shape of the box. So as you can see, the 1600 all the way to 0 is like some sort of normalization that is happening. So obviously, SPX has values that are 14, 1500. This is old data. I'm sure it's much higher now, but it can do the same thing. So if you look at Apple, there are a lot of outliers. There's so many dots that it looks almost like a line here. Okay. So Apple stock generally is, you might have to consider looking at it. The other, I'm going to do the histogram of this one. And looks like most of the Apple stocks are 4,000. So most of the distributions look all over the place, right? None of them is normally distributed. So we can do other form of histogram as well. So let's look at it, and it's going to run through that. And what we're going to do here is, use just so this is for every label. So you can actually see, 15 by 15 figure size, and it's going to go through everything. So as you can see, Apple, SPX, GNG. So it's looking at all the different things. And it's also correlating, right? So on here now we can, sometimes we don't want all of them. Let's just say we want just Microsoft, Johnson & Johnson, and IBM, and let's hit run, and it's going to capture something else. If you wanted something else, you could just do whatever company here is. That's a GE, and it should do the job as well again. Right, so we have 4 companies. So you decide what you want. So using it in an array and choosing it gives you stuff. As you can see, if you look at the data here, and the data has dates in it, and we can describe the data, a date, because there's no mean median mode for the date itself. So what we can do is drop it. So if you want to drop a column, you can say df1 equals d1 drop, and columns and name of the columns you want to drop, right? So I'm just going to like show you this. Let's comment this out for now and see df1 dot head dot to, and see how it changes the stuff. Remember, we had a date. Now we're going to drop the date, and there's no date here, right? So after we do that, we can just look at the correlation. This has already been run. We don't need to run it. Correlation is relationship between 2 variables. And if you look at American Airlines, and the way to read this matrix is American Airlines and it's exactly the same. It's always going to be correlated similarly. So American Airlines and Apple, they are correlated 10. So that means that positive 10. It moves in the same direction, but they are not super. But look at that AA and 91. So what this means is, think about it, when AA equals 1, GE is 0.90. So they are treating very similarly. It's kind of cool. So XOM and JNG are also correlated equally. So in some cases you see 1, but if you're standing in front of the mirror, you're always going to see yourself. So it's 1 means great, but if you're comparing against yourself, it's always going to be 1. But if you look at a different company, it looks like SPX and G are very closely correlated. So that's kind of cool. So in this one, what we'll be doing is visualizing the correlation. It is just, again, you can use SwiftViz or something else, and just correlation. So it's color coded. Full yellow means 1, and then a dark purple means 0. So look, if just, as opposed to looking at the numbers, it just pops in front of you, right? So yellow looks like JNG and PEP are highly correlated, and so forth. So you can just quickly look at it when you're doing data analysis. So you can also do the the function for KD, the probability function for Weibull and things like that for continuous variable. It is giving me error here. It's okay. Yeah, it is running. So you can do a lot of different distributions. Same thing, but we're doing a probability distribution for a bunch of different things here. Okay. Same thing. Try it out. And that's that there. So these are going to give you some values. So mu is a mean, and the sigma is the standard deviation. The value here, we're just hard coding it, and we're just going to run this to see when you give some certain value, this is what a normal distribution looks like. So most of the data is in here, some data is in here, and some data is in here as well. Moving along, there's another library called Seaborn. You can try that out. It's kind of like a matplotlib. You can import data set like this. Again, same thing, literally. And we can just, so when you get a message like this, essentially means that there's some error that needs to be deprecated, means it's going to be removed soon. Continue to use this, or you can choose something else. So in my case, I'm going to use it. So see that it it just did the pair plot of a distribution of same thing for different values and so forth. So this got a bunch of different information here. So you can try that out. I'm not going to go through each and everything, but you can try this out. The last one that I want to cover is something called log normal distribution plot. Again, we haven't gone it, but it's just log transformation, hit run. And again, it is giving you that line. So I know it is a lot to cover, but very least you should be able to import Iris, should be able to create data frame, should be able to run histograms, should be able to do box plot, should be able to describe the data, and then if need be, should be able to create random numbers. So the second part of the lab is a little advanced for our conversation, but I just wanted to give you some idea on how it needs to be done. All right, thanks a lot and enjoy trying it out yourself.